I guess, Niccolo, that we can start. Yeah.
Okay, thank you. Welcome everybody to the afternoon session. And it's my pleasure to introduce the first speaker of the session, Pravesh Kothari, who will talk about approximation schemes for a unit demand buyer with independent items via symmetries. And this is a paper co-authored with Divyarti Mohan, Ariel Schwartzman, Sahil Singla, and Matthew Weinberg. So maybe I'll say a few words about Pravesh. He's assistant professor at CMU Theory Group. He earned his PhD at Austin in 2016 and is the author of a monography on semi-algebraic proofs and efficient algorithm design. And he is also co-author of many good papers in Stockholm, Soda, Fox, and other prestigious conferences. Please, Pravesh, the stage is yours.
Okay. Thank you for inviting me to give this talk. So, I'm going to tell you about this very recent work on designing optimal auctions. But before I begin, I want to start with like a very short disclaimer. I'm not a full-time economist of algorithmic or non-algorithmic variety. And, both my interest, understanding of the problems, and whatever partial knowledge I have is basically completely due to, my amazing co-authors. There they are. And actually, I want to thank their patience for teaching me a lot of issues and, and clearing up the multiple confusions I had at various times, while we were thinking about this. So you may feel, a little bit shortchanged to listen to, an algorithmic econ talk from someone who is not an expert, but, hopefully I can still give you something interesting, and hopefully there will be some good things to take away from this talk for you. All right, so, this talk is about what could be thought of as perhaps the central question in, algorithmic mechanism design. And, it's basically the foundations of this area were laid by Nobel Prize winning economist Roger Myerson in his 1981 paper. And here's the most simplest version of this setting, okay? So you have, a single seller trying to sell a single item, let's say an apple, to a single buyer, okay? Now, we are in a game theoretic setting, so we have to at least, put some conditions on how the agents are going to behave. So we're going to assume, that the buyer is what is called as risk neutral and has quasi-linear utility. It's basically fancy terminology for saying the following, that the buyer has a certain value for this item that is being sold, and that they would buy it if the price of the item that the seller sets is lower than their value. And in that case, their utility, the value minus price, would be non-negative, and that's their only condition in which they will, buy the item. That's all this fancy terminology means. That's what, buyer is going to behave like. Now, our goal is to think from the perspective of the seller. So our goal is, to design a mechanism, a way to sell for the buyer in order to maximize their revenue, the amount of money they make, okay? Now, it turns out that Myerson in his paper already described in some sense a class of mechanism that turn out to be optimal. Okay, or at least, in some sense, he proved that only the following kind of mechanisms need to be looked at. And these are what are called as direct revelation mechanisms. Here is what that means. It means that, the buyer comes in, reveals their value, and then the seller quotes the price. And then, the buyer decides to buy if the price is lower, otherwise, go away. All right. Now, a priori, you might think, well, what's the big deal in this? The buyer reports the value. I'll set the price to be just a little bit less than the value. In that case, I'll obviously maximize my revenue, and that's it. Well, if you design your mechanism this way, the buyer will not really, join your auction because you're cheating, right? Like you're going to set the price depending on their value, and so there is no incentive in this case for the buyer to join. So what we force in that case, in order to make it meaningful for the buyer to join the auction, we force that the mechanism be what is called as incentive compatible. It's some version of truthfulness if you heard about it. All it means is that for either the buyer or the seller, there is no benefit that can be gained by cheating. So the mechanism should be such that you cannot win by cheating. Okay, so it turns out, and again Myerson proved this, that the only kind of mechanisms that actually satisfy this property are the following kind of mechanisms. So basically in these mechanisms, all that the seller can do is for every possible potential value that a buyer can have, set some a priori price. Okay, so the seller, before looking at the buyer's value, just decides on a function that places gives a price to every possible value that the buyer can have. They decide this a priori, right? Then just the buyer reports the value, and they choose the price from this list that they had compiled beforehand. Okay, good. So that's the kind of mechanism we're going to look at. This idea that one has to a priori decide a price as a function of the value is called taxation principle, or at least it's a consequence of what is called as a taxation principle. Good. So now, it turns out that if you're trying to do this mechanism design problem and you have absolutely no knowledge of how the buyer's valuation looks like, then there is not much to be done. It's also not surprising, right? Like if you're opening a startup, you probably want to do your market research. So, in this context, one thinks of the market research, or one thinks of your understanding of the market as, having some prior distribution on the buyer's valuation. So you have some understanding of how the buyer's valuation looks like in the form of a distribution from which the buyer's value will be instantiated once the auction begins. Okay, so in general, you only have the distribution D. The value itself will be drawn as a draw from the D, but you don't know that a priori. Okay, good. So that's basically the whole setting. You're given a distribution. Here's a single item, so it's a scalar valued random variable. Your goal is to design mechanism, which just means give me a price that you'll quote for all possible values in the distribution D, and that's it. That's your goal. So again, Meyerson, in the same paper, solved this problem correctly. And it turns out it's very simple to solve this problem. And what basically, what Meyerson observed was that, let's say, you sell the item at price V, then, the buyer will buy that with probability, which is, the buyer will buy that only in the situation when their valuation turns out to be smaller than the price you set. Okay. And the probability of that is precisely equal to this 1 minus f sub d of v, okay? Where f sub d is this probability that x is at most v, okay? And so this is called as the cumulative distribution function if you look at it. So so the way to decide on the best auction is to just maximize this expected value, okay? So that's the case of a single item, and Meyerson already told us how to do that optimally. We are going to be interested in the case of multiple items. So we're going to be interested in the case where the seller has n different items to sell. Okay. Now in this case, again following Meyerson, and again because things get very complicated if you don't assume this, we're going to assume that the value that the buyer has, the prior knowledge of this value that we have, is going to be a product distribution over each of the n possible items. What that means is that the value that the buyer will have will be chosen independently from for each item. Okay. Now, once this vector is encoded, we have to decide how the buyer is going to decide on a value of not just a single item, but also of a bundle, because for all we know, the buyer can buy multiple items. Okay. So in this work, in this talk, we are going to look at what is called as the unit demand buyer. All that means is that the buyer is interested in only buying one item. In particular, you can think of it as saying that the value of any bundle S is just simply, the maximum possible value of any item inside that bundle. Okay. So just to recall, because there's a lot of notations going on, there is a certain product distribution on a vector in n dimensions that gives you, in some sense, a priori value for every item. And for any bundle, the buyer values it as the maximum value of any item inside that bundle. Okay. And our goal is the same. We want to design an incentive compatible mechanism to maximize the revenue of the seller. Okay. That's what I'm going to look at. All right. So before going further, I want to just observe that, there are other kind of valuations you could consider. This is what is called as an additive buyer, in which case, the value adds, but let's not focus too much on this because I've already said too much notation. Good. So in this case, the same kind of reasoning based on what is called a taxation principle tells us that in some sense, the only kind of mechanisms we need to consider are the ones that really map really just, decide a price for all possible allocations. Okay, so let me be a little bit careful in describing what this means. Now, in general, remember that the buyer can buy any possible, subset of items. So in principle, I must give a price for all possible subsets. Actually, I'm going to go ahead and be slightly more general, and I'm going to define, allocations to even be what are called as randomized allocations or lotteries. What that means is that, given a vector in n dimensions, let's say a sub I, it represents a uniformly random set. It represents a random subset of items where each item is drawn independently to be included in the set with probability, AI of, j. Let's say the item j is drawn with probability AI of j. So each AI describes a randomized allocation. It's a distribution on sets of items, okay? And a menu, or basically the mechanism, is just going to describe a list like this. It's going to give an allocation and a price for it, okay? And in general, it can include multiple such potential allocations. And what Meyerson proved is that, the only kind of mechanisms you need to consider are the mechanisms that provide a list of potential allocations and the prices that the buyer must pay for them. Okay. And because it's like a list of, items that you can buy and prices for them, we call this list as a menu. Okay. Good. So you're up to speed with, 1981 stuff now. So, we are going to look at the algorithmic version of this problem, which means that, we have to decide what's our input and what's our output. I'm going to be still a little bit vague about this, but the input is going to be this n-dimensional product distribution. Okay. Now, if each of the DIs is, of finite and let's say some small size support, then you can describe this distribution efficiently by just giving each DI and then telling you that it is product. So at least there is some reasonable way to describe the input distribution, okay, which we assume is always known. The seller is going to decide on the mechanism based on the knowledge of this distribution. The output of this mechanism has to be this list of potential allocations and prices, okay? And just as before, we are trying to find out a way to design a mechanism, meaning choose a list of these allocations, prices that maximize the seller's revenue. Okay, good. So, once I set this problem, there's obviously two natural questions. How can we compute the optimal mechanism, given a distribution D, which is product, and let's say, small support, if you will, each DI has small support. How do you compute this revenue maximizing mechanism? And actually, even before that, we should be concerned about how are we going to describe it. A priori, the number of allocations is infinite. Even if you discretize, suitably, it's not going to be smaller than an exponential. So a priori, it seems like the kind of auctions we're going to look at will have exponentially large menu options. And this, in fact, goes by the name of menu complexity, the number of options on the menu. And so, before even computing the optimal mechanism, we also need to wonder about, how are we going to describe the optimal mechanism efficiently, or can we at all do this? Okay. So let me tell you a little bit about, what is known about this. And by the way, I'm still, believe it or not, in the 1981 paper of Meyerson. So here is what, Meyerson described. He basically completely described a optimal mechanism. The only flaw with this mechanism is that the time that it will take to compute this and the size of the description of the mechanism is going to be exponential in n, even when each DI has support of size at most D. Okay. So, here, if you look at this support of D thingy that appears in can be computed line, then that support of D is simply, if each DI has support 2, then D, the product distribution, has a support of size 2 to the n. And so this is, in some sense, you could consider a prohibitively large, mechanism or a menu, sorry. But anyway, at least it describes the optimal thing. So let me quickly run you through it. So basically, your mechanism, I told you, is going to choose a list of allocations, prices. So you can describe an allocation as just, mappings of various bundles to, so let's understand, the valuation, the valuation of the buyer looks like, some is described by some vector, n-dimensional vector drawn from the distribution D. So it's going to live in the support of D, right? And the allocation takes this valuation and outputs a distribution on sets of items. Okay. As I'm going to represent the set of items like I did on previous slide by a vector in the solid cube 0, 1 to the n. Okay. So any allocation takes a valuation vector and outputs a distribution on subsets of items. Okay. The value of this allocation is somewhat confusing notation. So again, let's be very careful. V of AV means the following. Remember, A of V is a distribution on sets. For, so what given A of V, I can now compute the value for the unit demand buyer when a random subset chosen from this, allocation A is granted to it. Okay. So this on the right hand side is just the definition of V of A of V. It's basically the unit demand buyer's value in expectation over the random subset that is given to it as a function of its valuation. Okay. So hopefully this notation is clear. So, okay, anyway, so, remember we are searching for, a menu of allocations and prices to, ask for them. So it turns out that we can basically write a very large linear program to compute this. And this is again, what Meyerson observed in his 81 paper. This linear program, it's a very simple linear program. It's just huge. It has basically variables for, in some sense, all possible. So, for each point in the support of the distribution D, I have to choose an allocation. I told you that the allocation is going to be a vector in 0, 1 to the n, the solid cube. So I'm going to make a variable for all possible A sub V's. Okay. And then, I'm just going to put natural constraints on it. The first constraint says that the value that a allocation gives an expectation to a buyer should be at least the price, meaning I should not set the price to be bigger than the value. Okay, so this in some sense is called as the individual rationality constraint. It basically is the constraint that, ensures that the buyer will at least buy the item. The second, the last constraint actually is what is the incentive compatibility thing we were talking about, that the buyer cannot, gain by misreporting their valuation. So for example, what this inequality says is, so on the left-hand side, I have, the utility that the buyer derives from the allocation given to it, when their valuation is given by the vector V. On the right-hand side, it's basically the utility they will derive when their true valuation is V and they misreport it by V prime. And so this constraint says that my utility should be larger on the left, meaning, if I tell the truth, my utility should be higher or at least not lower. Good. So this is an exponential size LP in any generic situation whenever the support of the, in support of DI is at least of size 2. And, but at least, it works. And that's what Meyerson proved. In fact, that of all possible monotone valuations, this LP gives the optimal mechanism. And so, the motivating question for this talk is, could there be a smaller menu? Do we really have to spend exponential size? And, in general, can we somehow compute at least the value of the optimal revenue that a buyer can gain efficiently or faster than exponential time? And so it turns out that the news is bad for this question. And let me not, run through this hardness results, what they mean, but basically, we know that exponential cost in the menu size is necessary, and that, we really can't hope to compute the optimal revenue. There are some complexity theoretic barriers to it. So, a lot of work has focused on approximating. And so, this kind of landmark work of Chawla, Hartline, and Kleinberg brought this, question into the TCS framework. And since then, like a number of works have focused on this. And the punchline of this works is to, design simple mechanisms that have, menus which are not too large and achieve a fixed constant fraction of the optimal revenue. But, it's a necessary, or it is a legit question to wonder if I can extract an arbitrarily large fraction of the optimal revenue. For any epsilon, can I get an 1 minus epsilon fraction of the optimal revenue possible with a small menu? And so, along that line, so far, at least, till about 3 years ago, we didn't even know that there was a finite size menu when, the distribution has infinite support. And so, in this work of Babayov, Gonsarovsky, and Nissan, they proved that at least, in some sense, there is a way to there's a clever discretization that at least gives you an exponential size LP, even when the distribution D has infinite support. Okay. And in some sense, that's really that's really the background I need you to know for, stating what we do here. Good. So now I can tell you the main result. Our main result is for unit demand buyers that I explained to you earlier. And what we show is that you can actually extract 1 minus epsilon fraction of the optimal revenue in quasi-polynomial time. Okay, so this is, basically an exponential improvement over known results, even for, DIs which have support of size exactly 2. Okay, And so that's the main result of this work. And in some sense, one immediate question you might have is, I already showed you that even for even for like very simple distributions of support size, each support size of DI is 2, the menu size has to be exponential. This is like a known result. And so in some sense, the first question you might ask by looking at this theorem is, what actually is the description of the mechanism that we can even compute? Clearly, we cannot compute the menu where we list all possible options and their prices, because it's not even possible in general to express it in quasi-polynomial size. And in some sense, that brings us to the key idea in this work, which is to define a class of menus which are compressible. Okay. And if I have like 3 minutes left, I'm going to explain to you what this idea is in a second. But basically, we're going to look at the symmetric menus, which have a compression property. We can compress them. We will show that, in fact, we can take, any menu and somehow, approximate it by a quasi-polynomial size symmetric menu. And then, we are going to show that we can use basically an analog of the same LP I wrote before to optimize over symmetric menus in only quasi-polynomial time. So that's sort of the key idea in this, is to, describe an alternate way to describe a menu. Okay. So let me, tell you a little bit about, how to think about this. Let's see. Okay, there we are. And so, in some sense, you can in fact abstract out this idea that we have of dealing with symmetric menus as a measure of complexity of a menu. Is some way to measure how large a menu is. And, in some sense, you can think of it as one of the main theorems in the result is that we show that, there is a quasi-polynomial symmetric menu that, approximates the gives a 1 minus epsilon approximation to the optimal revenue. Okay. So let me, spend some time, telling you a little bit, because, there are like lots of subtle issues. It took me a while to wrap my head around it myself. So, let me try to see if I can, convey this sense to you. So a priori, we describe menu as just a list of allocation and price pairs, right? And we were measuring the size of the menu by the number of, number of items in the list. And so a priori, this is just a question of, how large is it? How much space does it take to describe an optimal menu, right? And so, if you are like a naive computer scientist like me who does not know enough economics, you actually go to Matt and ask him, well, why are we doing this? Why can't I just describe the menu implicitly? Why do I have to, be explicit in the description as a whole list? And so, Matt, highly patient that he is, tells me that the reason we are choosing a menu to describe is, in some sense, we are somehow offloading all the computational cost to the buyer, sorry, to the seller here. In some sense, once I give the menu, the task that the buyer has is to compute their optimal strategy. If I describe the menu implicitly to them, then the task of computing the optimal strategy itself might become very hard. Okay. And so in some sense, the menu is being described as a list in order to make it very simple for the buyer to pick the optimal strategy for them. Okay, very good. Like, and in general, I guess one caveat to remember here is that the computational complexity of picking the best possible option in general can depend on the valuation function. If the valuation function of the buyer is complicated, then it may not be possible, under a given implicit description to compute it fast. Okay, so you say, okay, let's say, I only want to consider, let's say I still want to, push this idea of trying to implicitly describe a menu in some short way. So, one natural thing you might come up with is, well, we deal with approximations in our life all around. Why can't I just, why can't the buyer just approximate, the best possible option? Why do they need to compute it exactly? As long as we are able to approximate it, we should probably be happy. Well, it turns out that the IC constraints I told you before, the incentive compatibility, unfortunately, I won't go into detail of this, but basically, if your approximation is not with a factor of 1, then the mechanism is not going to be incentive compatible. And so basically, the summary of this discussion is that economics is tricky. By the way, this is a real discussion. This is real discussion that I had with Matt when I didn't understand what was going on here. Anyway, so it's kind of tricky to, come up with notions of size of menu, which somehow, do not somehow offload all the computational complexity to the buyer's side. And so in some sense, that's where in some sense our main innovation is, we come up with this notion of symmetric menu complexity that, allows the buyer to still optimize easily And there's actually a hope, and we prove for unit demand bias that there is in fact truth, that it can be actually sub-exponential size. So in the last 1 minute, I want to just explain to you what this symmetric menu complexity is, and I'll stop there. So, as I said, a menu, is just a list of allocation, price pairs. Let sigma be a subgroup of permutations of n elements, right? I'm going to call a menu symmetric if whenever a comma p is included in the menu, then so is any permutation of a and p for all possible permutations in this group sigma. Okay, in some sense you can think of it as the following idea. If in some sense, if two of the items are equivalent for the buyer, then in some sense, I can take any valuation function and, permute it around by, interchanging the values between those two items, and nothing will change. So this is, some symmetry between items. And, this symmetric menu definition is trying to capture this notion of symmetry between items. So one quick example to consider is if all items are equivalent, if you are perfectly symmetric under the whole permutation group Sn, then you can in fact describe the menu by simply giving the, price of bundles described only by size. You only have to give n+1 numbers. What's the price of 0 items, 1 items, 2 items, and so on up to n+1 items, and that is a complete description. And so the point is that if you use symmetries of the menu to describe it, then the description can become very, very compressed. And of course, in general, the sigma would be non-trivial, but we define the symmetric menu complexity to be basically the description of this subgroup sigma and the number of equivalence classes for the menu options. Okay. And the main result is to show that you can actually give a quasi polynomial sized symmetric menu to 1 minus epsilon approximate the optimal revenue. Let me not go into the steps because I'm out of time, so let me just stop here.
Thank you very much for your wonderful presentation. We have now time for some questions, so I invite all the attendees to write questions in the chat so that I can read them aloud to the speaker, that in turn can answer them, possibly. And offline questions may also be asked through the Slack channel. And in the meantime, let me say, which I forgot before, that this paper appeared in Fox 2019. So again, please write questions in the chat. Okay, so maybe in the meantime, as we wait, I may ask a question myself.
Yes.
Do things change when we have additive buyers or some other functions buyers?
Yeah, that's an excellent question. So, so in some sense, I didn't get to say anything about the proof strategy, but basically, the key non-trivial mathematical element of the proof is, to show that a certain Lipschitzness property holds for this revenue function. Like the value of this LP that I wrote before, we have to show that there is a certain kind of Lipschitzness property that holds for it. Now, this property really depends on the valuation function. And actually, when I started working on this, I thought it's going to be trivial. Like, how hard can it be to show Lipschitz of some simple functions like this? But it turns out it's actually very tricky. And we were able to show it only in the case of unit demand bias so far. And so, so far, we do not know that for additive bias, we do not know how to prove this Lipschitz property of the value of this LP. And, like, just for people who might be familiar, this problem, once you strip it off all of its detail, becomes, the problem of approximating a distribution by a symmetric, approximating a product distribution by a symmetric product distribution under a certain transportation distance. So, if you heard about the Wasserstein 1 metric, it reduces to a certain geometric task of approximating certain distributions. And, basically the metric that occurs in the unit demand bias is somehow natural and easy. So we were able to make our stuff work with that. For additive bias or for more general valuations, we don't know how to do it. And so, in fact, that is an open question, which a slide, I didn't get to.
Okay. I see. Thanks. So everything boils down to optimal transport once more. But not everything, but at least this important thing. Okay, yeah. So since I don't see questions from the attendees and we are out of time, then I would like to thank the speaker. Thanks a lot.
Thanks so
for,
much.
participating. And